Hello and welcome. In this video, we want to take a look at how we actually find potential functions if we happen to know we've got a conservative vector field. Okay, so I'm going to assume that we know that f is conservative. I'm just going to do it in 2D here. You do a very similar thing in 3D. And I want to find the potential function. That is, I want to find a function little f so that the gradient of little f, which is calculated as partial f partial x, comma partial f partial y, is equal to the vector field that we start with here, p comma q. So this gives us a couple of things to work with, because in order for these two vectors to be equal to each other, then the first component has to be equal to the first component there, and the second component here has to be the second component there. That tells me that the partial of f with respect to x has got to equal p, and the partial of f with respect to y has got to equal q. So I can get back to the function f by doing two different integrals. Now there's different ways people do this. Sometimes people integrate with respect to one and then differentiate that. Anyway, I just like to do both integrals. I like to say, take p, integrate it with respect to x. That should get me back to f. Take q, integrate it with respect to y. That should get me back to f. Compare those two results and take everything that I need to take in order to make it work. Okay, so let's do an example. Let's see what I mean by that. So I've got an example here. F of xy is p comma q, which is the p is 3x squared plus y plus 2x sine y, and the q is x plus x squared cos y plus 1 over y. Now, there's definitely a problem here when y is equal to 0. So that splits the plane up into two regions, everything above the x-axis and everything below the x-axis. And since I want this to be a conservative field, I need to know that I'm working in a in a open, simply connected region, right? So I'm going to just say, let's look at the top half of the plane. Let's let y be bigger than 0, because then that'll be a connected region. I could do it on the bottom half as well. I just can't take both, because if I take the top half and the bottom half but exclude the x-axis, that's not even connected, right? So I'm choosing here just to do the top half of the plane. We could come back and do the bottom as well later. But so first thing, I'm just going to double check that this is conservative. So I'm looking at the partial of this first one with respect to y, and then the partial of the second here with respect to x. So the partial of the first with respect to y, now that's just 0 plus 1 plus the 2x is constant, so 2x cos y, right? So 1 plus 2x cos y. Likewise, the partial derivative of this one with respect to x would be 1 plus, what is that, 2x cos y, remember the y is constant there, and plus 0. Both of those to give me 1 plus 2x cos y. So the mixed partials are equal, and I've got this on an open, simply connected region. So it is conservative. So now what I'm going to do is I'm going to do two integrals. I'm going to do two integrals. I'm going to say f is the integral of p with respect to x, or f is the integral of q with respect to y. Now I'm using, instead of dx and dy, I'm using partial x and partial y here, just to indicate to myself that this is sort of a partial integral. I'm saying it came from a partial derivative. So if I was taking a partial with respect to x, I was treating y as constant. So now I'm going to be integrating with respect to x, and again treating y as constant. Likewise, for the second one, I'm going to be integrating with respect to y, but treating x as constant. I don't think you'll find this notation very many places, but I like it when I'm doing these kinds of things, just to remind myself which is the variable and which is the constant here. So anyway, this is p that I'm integrating with respect to x. So integrating this with respect to x, 3x squared is going to integrate to x cubed. The y is just a constant, so that's going to become y times x, or x times y. And the sine y is a constant, but that's multiplied by 2x. So that's going to become an x squared times sine y. X squared times sine y. And then, because I was integrating with respect to x, I'm going to say plus a constant. But that constant could be any function of y. Right? Because any function of y, when I take its derivative with respect to x, partial derivative with respect to x, is going to be 0. So that could be any crazy function of y, or it could just be a constant, or it could just be 0, right? Depending on what is needed for the other integral. So now looking at the other integral, I'm going to take q and I'm going to integrate that with respect to y in order to get to f. So here's q, x plus x squared cos y plus 1 over y, integrated with respect to y. So the x squared integrated with respect to y is x times y. The x squared cos y integrated with respect to y is x squared sine y. And then the 1 over y would integrate to the natural log of y. I don't need an absolute value here because remember I've assumed that y is positive. So I'm just saying log y. And then plus a constant, but here the constant could be any function of x. Because again, going the other way, if I was taking the partial with respect to x, if I'm taking the partial with respect to y, anything that's all just x's is going to turn into a 0. Okay, so that k of x could be any function of x, anything crazy or anything very simple like constant or 0, depending on what the other integral required. So now I look at all the pieces that I need, right? This first one said there should be an x cubed, there should be an xy, there should be an x squared y, and maybe some stuff with y's in it. The second one said there needs to be an xy, there needs to be an x squared sine y, and there needs to be a log y, and maybe some stuff with x's in it. So the first thing I notice is that both of them say you need an xy plus x squared sine y, right? So that's this. The first integral says I need an x cubed, and notice that that could also play the role of this k of x in the second integral, okay? So if I include the x cubed, I've also included the k of x for the second integral. Likewise, on this second integral, it says I need a log y, but that log y could play the role of the c of y in the first one. So all the pieces that I need are, I need the x cubed, I need the xy, I need the x squared sine y, and I need the natural log of y. Right? If I have all of that, then both of those integrals would be satisfied. And in fact, this right here, this f of x, is a potential function for that, that conservative field. A couple of notes here is I could include a plus c on this because adding an actual constant wouldn't change any of the partial derivatives. So there isn't just one antiderivative. There isn't just one potential function. There's any number of them, but they only differ by a constant. Now, typically, we're doing this when we're trying to solve a line integral, and we're going to be plugging in endpoints and subtracting. So that plus c is irrelevant because it gets subtracted out. It gets added in and then subtracted out, and it goes away. So for the most part, you don't have to worry about the plus c because we'd be doing definite integrals. And another note here I just want to point out is a very common mistake is people just add the two results. And the problem is if you add the two results, then because the xy plus x squared sine y is in both of them, you would end up with a 2xy and a 2x squared sine y, and that just throws the partial derivatives off. It's not, you don't get the right derivatives to be the gradient doesn't become f anymore because you got those extra 2's in there. So you're not adding these two results together, you're combining them. You're taking all of the pieces that each one says needs to be in there. Okay? And if this was conservative to begin with, then they should match up very well, right? If they're telling you completely different things, then it's like, okay, maybe I should go back and double check to see if this is conservative. But if it is, if you already know it is, then these two things should match up pretty well. And really the trickiest part of it is just recognizing that this x cubed that doesn't look like it appears in the second one is there because it's the k of x, right? Well, likewise, the log y down here didn't appear up there, but there's a spot for it in that c of y. That's some function of y that you don't know what it is, but it could be anything. Well, the other integral is telling you what it could be, what it is. So anyway, there you go. There's a method for finding potential functions if you know you have a conservative vector field. Enjoy.